Hi, welcome. This is Dr. Ravik Pradhan, Assistant Professor, Department of Mathematics, School of Basic and Applied Sciences, Advanced University. So, in this lecture series, we are talking about the basic probability theory. So, in last two lectures, we have talked about the set theory, basic definitions, operations on sets, and then algebras of sets, and we talked about the definition of the sigma. So today we are going to discuss about the basic definitions of the probability which are related to random experiment, what is an event, what is the sample space, and what is the definition of probability. And then few theorems related to them, how to assign the probabilities corresponding to it. So the first thing is, what is an experiment? Experiment is an activity or process. Now, there are two types of experiment. One is deterministic or certain experiment in which the outcome is certain or deterministic. Like for example, if I consider a chemical experiment like mixing of uh, the alkali that is uh, NaOH and an acid HCl, if I mix them, will have salt, NaCl, and H2 water. So we know what are the outcome corresponding to that experiment. But if I consider an experiment of tossing a coin, then we do not know what is going to happen in a in a particular uh, occurrence of that particular experiment, conduction of that experiment. We do not know what is the outcome. But if I consider the experiment of tossing a coin, we know what are the possible outcomes. I know that it is going to be head or tail. So the possible outcome of the experiment is known, but what is the particular outcome going to come in a performance of the experiment, we do not know. So those experiments are not certain or deterministic. They are called random experiment or statistical experiment. So formally, a random experiment or statistical experiment is an activity or process in which all outcome of the experiments are known in advance. Like for example, if I consider the tossing a coin, that we know that we are going to have either head or tail. So two possible outcomes are there. The second condition says that any performance of the experiment results in an outcome that is not known in advance. So, if I toss a coin, I do not know whether I am going to get head or tail. So, that outcome of a particular performance of the experiment is not known in advance, but we know what are the possible outcome of the experiment. And the third condition says that the experiment can be repeated under identical condition as many times as we wish. That means we can toss the coin as many times as we wish. Under the same condition, the experiment can be conducted as many times as we wish. Okay, so these are the three conditions. If these three conditions are satisfied by a process or activity, then that experiment or the process is called random experiment or statistical experiment. So, for example, I have already mentioned the example of tossing a coin. If I consider the experiment of rolling a die, in that case also, we know the possible outcomes are 1, 2, 3, 4, 5, or 6. So all the possible outcomes corresponds to this experiment are known in advance. but we do not know what's going to happen in a particular performance of the experiment. That means if I roll a die, we do not know whether it is going to be 1 or 2 or 3 or 4 or 5 or 6. But these outcomes are known to me in advance. And I can conduct this experiment as many times as we wish. So this is a random experiment or statistical experiment. Similarly, if I consider a roulette wheel in which there are 38 divisions or sections and different scholars are there. The sections are like 0 to 36 and double zero is there. So in these, actually, a person can bet on any combination of these numbers or colors. There are colors like red or black are there, so you can bet on that. And a ball is there. A ball is there which is rolled on the edge of this wheel, roulette wheel, and in the opposite direction. And wherever it stops, that result will be the outcome of that experiment. And in this experiment, there are, if I think about the only numbers, there are 38 possible outcomes, 0 to 38 and double zero. That is 38 possible outcomes are there. But in a particular experiment or in a particular performance of the experiment, we do not know where this ball going to stop. So this is also a random experiment. And also we can actually, the third condition says that we can conduct the experiment as many times as you wish with the identical conditions. So we can do that thing. Now let us go for the fourth example, whatever I have mentioned here, that is the length of the life of a light bulb produced by a certain manufacturer is recorded. So if I think about the lifetime or life expectancy of a light bulb of a particular brand, then that is also a random experiment. Because if I take a light bulb and uh, put it under the electricity, then it may immediately fail. That means the bulb got diffused. That can happen. So the life expectancy of that bulb is going to be 0, or instantly it stopped working. Or a bulb can work for thousands of hours. So the lifetime or life expectancy of the bulb can be from 0 seconds to many hours. So we can think that as infinity. So the life expectancy of the bulb can be any number between 0 to infinity. So we know what are the possible outcomes of this experiment. But for a particular or for a randomly selected bulb, if I perform this experiment, we do not know what is going to happen. We do not know how much time the bulb will work properly. Okay, so this is also an example of the random experiment. So I have mentioned here 4 random experiment, out of which you can see the first one, there are 2 possible outcomes. If I think about the notation, I can write head and tail. For the second one, I have 6 possible outcome: 1, 2, 3, 4, 5, and 6. If I think about the third experiment, there are also 38 possible outcomes: 0, 1, 2 up to 38, and double zero, 38 possible outcome if I consider only the numbers. But for this fourth experiment, the possible outcome can be any number between 0 and infinity. So I've taken this example purposefully because to understand the fate corresponds to these random experiments. Now, if you look into these first 3, they are actually countable. I can see in the first experiment corresponding the possible outcome, the set corresponding to the possible outcome contains two outcomes only. For the second experiment, we have 6 possible outcomes. For the third one, we have 38 possible outcomes. For the fourth one, we have infinite number of possible outcomes. Rather, I should say it have uncountable number of outcomes. Okay, so let us see what they say or how we can understand this thing. So let us go to the definition of sample space. Now, what is the sample space? Sample space is is a pair. It's a pair corresponds to the set of all possible outcomes. So here I have mentioned, I have used two notations, omega and fifties. Omega represents the set of all possible outcome corresponds to a statistical or random experiment. And fifties represent the sigma field or sigma algebra of subsets of omega. So this omega is means the elements of this omega are called the sample points. So sample space is nothing but a pair which consists of the first element of the pair is the set of all possible outcome corresponds to a random experiment or statistical experiment, and the second component of this pair, that is fifth is the sigma algebra or sigma field corresponds to that particular set omega. Okay. Now, how we can construct the sigma algebra or sigma field we have already seen. So if I have omega as a set, then I can consider the all possible subsets of omega and omega itself and the null set. If I consider this collection, that will be the sigma algebra or sigma field corresponds to this omega. So these two things, two things as a pair is the sample space corresponding to a random experiment or statistical experiment. Now, we have already seen 4 examples in the last. Among those 4 examples, we have seen in 3 examples, first 3 examples, there are the possible set of possible outcome is countable set. Okay. So those set or the sample space corresponding to those experiment are discrete sample space. And in the last example, that is the life expectancy of the light bulb, we have seen the set corresponds to the all possible outcome of that experiment is an interval, which is an uncountable set. Those experiment or the sample space corresponding to that experiment is called continuous sample space. So there are 2 types of sample spaces. One is discrete sample space, where the set of all possible outcome, which is a omega, is having a finite number of points or at most a countable number of points, sample points. Then the sample space is the discrete sample space. If omega contains uncountable many points, then the sample space is called continuous sample space. So in the example of tossing a coin, we have the discrete sample space. In the example of life expectancy of a light bulb or life expectancy of any electronics item or life expectancy of human being also is corresponds to continuous sample space. Now, once we know what is a sample space, we are in a position to define an event. Event is a non-empty subset of the set of all possible outcome omega. So you can see that event is a subset, non-empty subset of the set of all possible outcome omega. which is a disjoint union of single element subsets of the sample space omega script S of a random experiment E. Okay. So if I think about an experiment of rolling a die, the corresponding sample space will be the set that omega is equal to 1 2 6 1 2 3 4 5 6, and that script S, that sigma algebra corresponds to it, will be the power set of that omega. Now if I consider the event as getting an even number as the face of the die, then if I consider this event E equal to, sorry, if I consider the event A is equal to getting an even number as the face of die, then what will be this A? This A can contain even number 2, 4 or 6, which is a subset of this omega, which is the set of all possible outcome of the set of this experiment. So event is a subset of the set of all possible outcome omega. Now if I think about the event could be of two types: simple event and composite event. Simple event means the event which consists of only a single element. For example, if I say it means if I toss a coin, in the experiment of tossing a coin, my event is getting a head. So getting a head A, if I consider the event, then it contains only singleton each. So it's a simple event. Now if I think about the composite event, here is the example of the composite event. This A, getting an even number. If I consider the experiment of rolling a die, then if I consider the event A as the getting even number as the face of the die, then it consists of several points. It is the composition of several single events. Like it consists of the single event getting a 2, getting 4, getting 6. It is the composition of these three things. So it is the composite event. Okay. So sample space is nothing but the pair consists of the set of all possible outcome, and the sigma algebra or sigma field corresponds to that set of all possible outcome. And they are of two types. One is discrete sample space, where the sample space consists of countable number of elements. That means it is corresponds to a random experiment where we have only countable number of possible outcomes. And in the second case, we have the continuous sample space. In the continuous sample space, we have uncountably many points, uncountably many sample points. Okay, so and then we have the definition of event. Event is nothing but a subset of uh, the subset of the set of all possible outcomes. Okay, so next we are going to define the probability. So here are the some examples we have already mentioned. If I think about the random experiment, which is tossing an unbiased coin, then set of all possible outcome is going to be head and tail, and the sigma algebra corresponding to it is going to be the null set, and the set itself and head and tail. In the second example, if I consider the experiment of tossing a coin until the first head appears, then the set of all possible outcomes consist of first head. That can be one possible outcome. That means in the first toss I got the head and the experiment stopped. In the second outcome can happen also. That means the experiment is getting head Means whenever we got the first head, we stop the experiment. So in the first possible outcome is that in the first toss I got head. The second possible outcome is that in the first toss I got tail, in the second toss I got head. So that could be another possible outcome. Similarly, I can get two tail followed by head, then three tail followed by head. So these are the possible outcomes of this experiment. So omega could have these elements, and observe that this omega is a countably infinite set, because I can relate this set, or I can map this set with the set of natural numbers. Because in the first one, you can see the number of toss required to get the first head is a natural number. The first element relates to 1. The second element, the number of toss required to get the first head, that is 2. The third element is related to 3. The fourth element is related to 4, and so on. So we can relate this omega with the set of natural numbers as 1, 2, 3, 4, and so on, which is the number of tosses required to get the first head. It is means countably infinite set. Infinite number of elements are there, but it's a countable set. Now, if I uh, think about the sigma algebra, it will be the set of all subsets of the positive integers. So it have infinitely many elements, and here also the sample space corresponds to this experiment is again discrete, like the first one. In the first example also we have uh, the discrete sample space. In this case, in the second example also we have the discrete sample space. Let us go for the third example. It's a bit different from the last two examples. In this example, we have considered a point which is moving or spinning around a point, around a fixed point by a circle. Means the path of the point is a circle. So a pointer is free to spin about the center of the circle. If the pointer is spun by impulse, it will finally come to rest at some point. So, and some external forces act on that pointer, so that the pointer comes to an stop, or comes to rest at some point. Now, if you think about this experiment, this pointer stops somewhere which is random, because we do not know how, means when this pointer is going to come to rest. So if I think about this experiment, this all possible outcome correspond to this experiment will be the set of 0 to 2 pi r, because the point can stop somewhere within this range, where r is the radius of the circle, and every 1.6 x is a simple event. Means the point where the this pointer can stop. The event of interest are those in which the pointer stops at a point belongs to the specified arc. That means it will stop somewhere in between these, means in between this, on the arc it will stop somewhere. So here S is taken as the Borel sigma field of subsets of 0 to 2 pi. So it's an interval. So in this case, infinite means it's an uncountable set. So this set is different from the last two, means the set of all possible outcome of last two examples. So in the last two examples, we have the discrete sample space, but in this case, we have continuous sample space. Okay. So we have the idea of the sample space of a random experiment, and then we have the idea of event. Now we are in a position to define the probability of an event. So if I consider the example of tossing a coin, and if I toss a coin, we know that there is 50% chance I'll get the head, there is 50% chance of getting a tail. Now, this is the assignment of probability. That is not the definition of probability. If I want to define the probability, I have to have some systematic way to define the probability. So here we have the definition of probability, which is given by the Russian mathematician Kolmogorov, which is known as the axiomatic definition of probability. It says that if I have a random experiment and corresponding to that random experiment, the sample space is given by omega script s, where omega is the set of all possible outcome and script s is the sigma field or sigma algebra corresponding to it. Then a set function P is defined on script s, which is the sigma algebra. So P is a set function from sigma algebra, or rather I should say sample space, is called a probability measure if it satisfies certain conditions. The conditions are or axioms. The first axiom is that probability of a set is greater than equal to 0. Here, the set is corresponds to an event. So the first axiom says that the probability of an event A is greater than equal to 0 for all the event A, which is a subset of the set of all possible outcome, which belongs to the sigma field. So the first axiom is known as the axiom of positiveness. That means the probability of any event is going to be a positive number. Second axiom says that the probability of the set of all possible outcome is going to be 1. That is called the axiom of certainty. The probability of all possible outcome of the experiment is going to be 1. Third axiom says that if I have countably infinite number of events of the experiment which are mutually exclusive or disjoint, then the probability of countable union of those events is equal to summation of probability of those individual events. So here there is a printing mistake. It must be probability of AJ. So I have a random experiment corresponds to it. The sample space is omega comma script s. Then probability measure is a set function from the sample space to the real number set, which satisfy 3 axioms. Axiom of positiveness, which says that the probability of any event is greater than equal to 0. Second axiom, which is the axiom of certainty, it says that probability of set of all possible outcome is equal to 1. The third axiom, the axiom of countable additivity, is that if I have a countable disjoint sequence of states AJ, then the probability of the countable union of those sets will be equal to summation of probability of individual events. So that here we have the assumption that those sets are going to be disjoint or mutually exclusive. So if some function satisfy these 3 axioms, then it will be a probability from the sample space means it will be a probability measure for that random experiment. And these three things together, that triplet, this omega, tryptase and P, probability measure P, is called the probability space. It creates the probability space here. Okay. Now here you might have a question that uh, then from this definition, how we can find the probability of an event? Okay, so that thing we'll discuss in the next video. So in the next video, we'll talk about how to assign the probability corresponds to an event and related theorems. So till then, see you. Bye bye.